All right, hello everybody. We are going to look at 2.7 today, limits at infinity. So as a quick warm-up, I want you to use this graph to determine one-sided limits. Okay? So pause this video. I'm going to fill in the answers for you, but try to pause it and do it on your own. So limit as x approaches 2 from the left. So I'm looking over here. And that is approaching 3. Limit as x approaches 2 on the right. That's going down to negative infinity. So therefore the limit as x approaches 2 does not exist. The limit as x approaches 1 from the left is approaching 1. 1 from, oops, I'm sorry, I did negative 1 there. Okay, so 1 from the left is approaching 2. 1 from the right is also approaching 2, and therefore the limit is equal to 2. Function value doesn't exist, or I'm sorry, the function value does exist up there at 3. Doesn't match, but that's okay. The limit exists. That just means that this is a discontinuous function at 1. Okay, so far we've discussed limits at a particular x value, such as x approaches 5. But today we're going to look at, well, what about as x approaches values like infinity or negative infinity? Okay. So first of all, a little bit of notation. Limit as x approaches infinity of a function equals a value L, a number L, if f of x gets closer and closer to L as x approaches infinity. The limit as x approaches negative infinity of f of x equals L if f of x gets closer and closer to L as x approaches negative infinity. So what effect will this be on the graph? What do you think? So if you're thinking perhaps similar to an asymptote, you're correct. Now we looked at limits at values that gave us answers of infinity or negative infinity. Now we're kind of reversing that idea. So instead of a vertical asymptote, this would imply that we are approaching a horizontal asymptote. So for example, if I have the limit as x approaches infinity equaling 2, as well as the limit as x approaches negative infinity equaling 2, that implies that I must have a horizontal asymptote at 2. So this is just one example of what this might look like. Okay. So on the far right of the graph does go on forever, and it approaches the y-coordinate of 2. Same idea on the far left side of the graph. Graph goes on forever, and it approaches the numerical value of 2. So let's investigate this. Theorem 1. For all n greater than 0, so if the exponent is positive, right? If the n is positive based on these definitions, limit as x approaches infinity of x to the n power would go to infinity, right? That would continue to grow. Limit as x approaches infinity of x to the negative n power, which is the same as 1 over x to the n, would go to 0. So if we have a negative exponent, it means it's in the denominator. So we have some number divided by something very, very large that approaches 0. Okay? And then we have to look a little bit more, specifically on the negative side of the graph. Okay? So the limit as x approaches negative infinity of x to the n power, again, n is positive here. So there's two different answers here. If n is even, so if we're looking at an x squared or an x cubed, x to the 4th, x to the 6th, etc., the negative infinity would go to positive infinity, right? If n is odd, though, cubed, 5th, etc., the negative infinity would remain negative, and it would go to negative infinity. if we look at negative infinity and we have a negative exponent, right, so we really have a rational expression or function, then it will always go to 0. So anytime we have x to the n in the denominator, whether x is growing positive or negative, the limit is 0. So at the bottom, I just have some examples to help us kind of investigate this. We don't really need to think about the actual numerical answer, but you can if you want to. So if we were to look at negative 100 and we square it, the biggest thing that we need to acknowledge is if we square a negative number, it goes positive. Right? It goes positive 10,000. We could continue with this and acknowledge that all of these go positive to 1,000,000, and so forth. 3, 4, 5, 6, 7, 8. 100 million. But if we do the same idea with cubing them, right, it's going to be a negative value, a negative number. I'm just going to write that for the sake of time. Again, negative number, larger, larger, negative number. And if we have the negative exponent over here, it's 1 over a number, a large number. The key is that we have something growing and growing and growing towards infinity. So it's either a number growing to positive or negative infinity, or 1 over positive or negative infinity, which will always equal 0. Or approach 0, I should say. Okay, so we're going to investigate this a little bit further, and then you're going to be able to establish rules. When we are looking at limits as x approaches infinity, most of the time we are doing this with a rational expression. Okay, so it's a division problem, right? The shortcut, in order for us to investigate this, we've kind of learned over the years that the largest degree, the largest terms are the ones that have the impact on the end behavior of our graphs, right? The extreme values. So we're gonna divide by the highest power of x in the denominator, right? So it's the division problem. We acknowledge that x to the 5th is the largest term in the denominator. So we're going to divide every single term in this rational function by x to the 5th. And rather than writing it as a division problem, because that can look a little bit messier, I'm going to write it as multiplication of x to the negative 5th. Right, so I'm not changing the value of anything, because what I'm doing is I'm multiplying top and bottom by the same. I'm picking x to the 5th because it is what would have the largest impact on this division problem. Okay, so this will allow us to analyze the end behavior much more easily. Okay, so we simplify this. So now we have 20x to the negative 3rd. We have minus 3x to the negative 4th. We have 3 minus 4x to the negative 3rd plus 5x to the negative 5th. And then, of course, I should be squeezing. We're still thinking about the limit as x goes to infinity of this. Okay, so not always, but for right now, I'm going to rewrite this using fractions instead. So the rules that we just established, right, you're seeing negative exponents. So now we want to analyze what would each of these terms become, right? Would they zero out? Would they go to infinity? Would they go to negative infinity? So I'm going to rewrite this as a complex fraction right now, just because I think looking at 20 over x cubed is a little bit easier to comprehend than looking at it as a negative exponent. Okay, so now what I want to acknowledge is that every time I have a numerical or a number in the numerator divided by an x term, if we conceptualize that and think about it as x is going to infinity, so I have 20 divided by infinity cubed. Small number divided by huge number always goes to 0. So every single term in this complex fraction that is written as a fraction with, right, x in the denominator is going to zero out because the denominator is growing so fast and that number up top is minuscule in respect to that. So the result simplifies here to 0 over 3. Well, that's 0. So, therefore, this rational function, if we look at the far right-hand side of the graph's behavior must be approaching the value of 0. Okay, let's try another one. Divide by the highest power of x in the denominator. So that is just x in this case. So we're going to multiply top and bottom by x to the negative 1, which is the same idea as dividing by x. So this will give us a 9x minus a 2x to the negative first, divide by a 6x to the negative first, minus a 29. Okay, every term is important. Okay, so now we need to analyze what will happen at each of these terms as x grows to infinity. So I'm going to rewrite as some fractions, some complex fraction here. Okay, so now if I input infinity to each of these terms, the first term is 9 times infinity. That conceptually grows to infinity. The second one is 2 divided by infinity, so that's a 0. 6 divided by infinity, 0, and a negative 29. So we have infinity on the top divided by negative 29 on the bottom. Super important that it's negative because the overall answer is negative infinity. All right, same idea. It looks a little bit harder because we're starting with some fractional exponents. So still, we identify the largest power in the denominator and we divide through by that. So that would be x squared. So multiply through by x to the negative second. You can also think of that as negative 4 over 2. Right, so then we have a 3 over 2, negative 5 over 2, one, and negative 3 over 2. Okay. Positive exponents will grow to infinity. Negative exponents will go to 0. Result is infinity divided by 1, which is infinity. Take the time to work through these. We'll go through these in class. I'm not going to put the work up here. I'm going to give you the answers right now just so that you can make sure that you did do them correctly. And also, while you're working through these, see if you can establish a rule, right? Because we don't want to have to go through this process the entire time. You might have already started to acknowledge that there's probably a rule for this. And there is. And this rule is exactly the same rule that we established in Algebra 2 and again in pre-calculus when we were analyzing the rules for horizontal asymptotes. So if the degree of the polynomial in the denominator is higher, the limit is 0. Simply put, the denominator is growing faster. Therefore, we have a situation where it's small number divided by a huge number, which approaches 0. So if I simplify a rational to ax to the m, obviously with other terms, over bx to the n with other terms, we are always using the largest term top and bottom to analyze this. So and this is the scenario, let me change colors, to n being greater than m. If the degree, second case, if the degree of the polynomial in the numerator is higher, then the limit is either positive or negative infinity. This example, we got negative infinity. What you need to look at here, much more closely than the other scenarios, you need to take the leading terms means highest exponent, and simplify it, right? 9x squared divided by negative 29x. That results in a negative 9x over 29. So the fact that the coefficient is negative is what's going to tell us that this is a negative infinity scenario. Unless, of course, right, be careful, I was actually evaluating this limit at negative infinity. So then I would be doing a negative times a negative, and it would go positive. So you have to be more careful in case 2. Case 3, they're the same. You would get 3 over 4 for this example, right? They are growing at the same rate. The x squareds cancel out in this scenario, and you would have 3/4. So these are your 3 different situations. If the bottom is larger, 0. Top is larger, some form of infinity. The same leading coefficient. So you try. All we're doing is taking a look at the largest terms, top and bottom. We don't care about anything else. Bottom is larger here. It goes to 0. It doesn't matter if we're talking about positive or negative infinity. In both cases, it goes to 0. Second scenario, or second example, they are the same, x squared. So we take 2/3. The top and the bottom are growing at the same rate, so the impact is coming from that 2/3 ratio. Last one, simplify that. Top is larger, so it's going to be some form of infinity. So we're looking at an x over a 4. At negative infinity is super important. So that's like having a negative infinity over a 4, which simplifies to a negative infinity. All right, I'll call it a hiccup to this process, right? What if it gets a little bit more complicated? So for x being greater than 0, okay, the limit as x approaches infinity of something like this. Well, if I take a look at the largest terms like we've been doing, I have a 12x and I have the square root of 16x squared. Right? So we naturally want to just say, oh, this is 12x over 4x, which is just 3. So that's all fine when x is positive. Okay? When x is positive, we are fine. And therefore, on the right-hand side of this graph, sure, we approach an asymptote of 3. But how come we go down here to negative 3 on the other side? Right? So we have to think about this. The square root of 16x squared equaling 4x. Well, couldn't it also equal negative 4x? How do we analyze this? Think about it like this. If x is negative, right, how do we make this hold true? Because if x is negative, let me use it like negative 1 as my example. Putting question marks because which one is going to be a true statement here? So if x is negative 1, I'm going to have negative 1 squared is 1 times 16. I'm going to have the square root of 16 equaling 4 on the left-hand side, equaling negative 4 on the right-hand side. So that's a false statement, which means that when we're looking on the left-hand side with even roots, if if we're looking at negative values, we have to negate, kind of like double negating, because if I'm going to input a -1 and I want this to be true, then I need to have a negative out in front so that it turns it back positive, right? So, I mean, we've been learning all of the time when you're taking the square root of something, you need the plus and the minus, right? This is the example of why. The negative, the minus solution, is actually negating the negative that could be there, okay? So it's kind of a hard concept to wrap your head around. We will definitely look at this in class and talk about it more. Live in person would be more helpful. But what you're going to do here is, if you're looking on the left-hand side, negative numbers, if you have that even root, you're going to say, well, this is 12x divided by -4x to make it a true statement. And then this simplifies to -3, and that's where it would come from. So it's all about whether or not the statement would be true if I used a positive or a negative number, right? Does 16x squared, square root of that, equal 4x always? Or does it sometimes equal the positive, sometimes equal the negative? All right, looking at this example, we are specifically looking when x is negative here, x is less than 0. Okay, now, the previous example, when I simplified the square root of 16x squared, simplified to 4x. Now I need to analyze this and say, well, is this always true? Does the square root of 16x to the 4th always equal 4x squared? Well, let's test it with the negative, because that's where the problem would be. So let's just use -1. Is this a true statement? Yeah, it is this time. And it is because when I simplified, I still had an even power. So it's all about whether I simplify and I have an even or an odd power coming out of that square root. So now when I go and look for this answer, I'm looking at 8x squared divided by 4x squared, and I can follow my rule, right? This simplifies all the way until 2, the ratio of the leading coefficients, because the degrees were the same. Here's another example. We're looking on the left-hand side. We're looking when x is negative. Here's our leading terms. If x is negative, does square root of 4x squared always equal 2x? Okay, well, let's use our negative number. 4 times -1 squared, square root of that, does it equal 2 times -1? And in this case, it does not, right? The left-hand side comes out as +2. The right-hand side comes out as -2. Since it didn't work, we need to negate the right-hand side for values less than 0 to make this a true statement. So when I'm finding this limit as x approaches -infinity, I'm really thinking about x divided by -2x. Degrees are the same top and bottom, so my answer is -1/2. Okay, so this same exact idea can help us with a different set of instructions. So here they're just saying find the horizontal asymptote. So this really could just be an Algebra 2 question. Sometimes we have to think about one-sided limits to figure out whether this is true or not, like one-sided limits at infinity. In this case, if we have 4x cubed over 8x cubed, we know the degrees are the same, and it's going to bring us to 1/2. There's no square roots, there's nothing else happening differently, so it would not matter on the left or on the right. Okay. The second one, though, right, we need to think about what's happening on the left and on the right. Is it different behavior at positive or negative infinity? Yes is the answer to this, because when I simplify square root of 16x squared, it simplifies to an odd power. It simplifies to 4x. So we need to think about it as plus and minus 4x divided by 3x, which would give us plus and minus 4/3. What we did is we thought about the limit as x approaches negative infinity, which would give us the negative 4/3, and the limit as x approaches positive infinity, which would give us the positive 4/3. So these are your horizontal asymptotes. Okay, I'm going to leave this one up for you all. See if you can figure out what those horizontal asymptotes are, and we'll talk about that in class. 3 main cases. Look back in your notes in order to summarize that. And how can you use limits to find horizontal asymptotes? All right, big lesson. Nice job. There's a lot of tough things in there, so you might want to watch this a couple of times.